Welcome back to another AP Physics 1 topic overview. Today we're going to be talking about circular motion. So let's get right into it. Alright, so circular motion is just really an extension of Newton's second law, so that now we're going to have an equation for acceleration in a circle. So an object moving at a constant speed v in a circle of radius r has an acceleration of magnitude v squared divided by r directed towards the center of the circle. So remember, going back to equilibrium, we talked about that an object moving in a straight line at constant speed, that's an object that is going to be in equilibrium. My forces are going to be balanced. We say in a straight line because when we have circular motion, we are moving at constant speed, or when we have uniform circular motion, we're moving at constant speed, but we are constantly changing direction, so we are accelerating. So that's the distinction between the constant speed in a straight line versus constant speed in a circle. And I have the equation there just written out again, just for a little more clarification. A subscript c equals v squared over r. So let's move into our other facts. So Newton's second law, we've seen this before, but just to refresh us on what exactly it is, whenever we do any problem with forces, we draw a free body diagram first, then we write two equations if we have both up and down forces in the free body diagram. So again, with this, we do up forces minus down forces equal ma, left forces minus right forces equal ma. Below this, I have F net equals ma. Remember that the unbalanced force, or the value of the unbalanced force, is the same exact thing as the net force. So whenever they say net force, just interchange that with unbalanced force, and that actual value for the unbalanced force is the up forces minus down forces, or left forces minus right forces. Note again, we don't want to have negative values here, so we are going to start off with whatever force is in the direction of acceleration. So if my acceleration is downwards, I start with the down force first, then subtract the up force. So we're going to see that in these examples here today. So let's move into our last facts here. So again, just a reminder of what a free body diagram is. It's a label arrow that represents each force. This arrow begins on the object and points in the direction in which the force acts. We're going to go through this each time that we have a situation here, draw the free body diagram of the situation, and we're going to have a list of forces indicating the actual object that is creating the force on the other object. So remember again with this that we have to be in contact with an object in order to experience a force from it, unless it is the force of Earth on the object, more commonly known as the weight, or Fg. So let's get right into our example. All right, so moving into example number 1 here. So again, with all of these examples and the facts, they're in the description down below as Google Docs. So you can choose to do it along with me, or you could then do it yourself, jump to the end of the chapters and see if you got the answer correct or not, whichever way you feel like doing it. So in this first example, we have, while driving along a country road with a constant speed of 10 meters per second, you encounter a dip in the road. The dip can be approximated as a circular arc with a radius of 10 meters. Your 80 kilogram passenger sits in the seat next to you. So what we're going to do here first, the dot right below represents the passenger sitting in the car while it moves through the bottom of the circle. We're going to draw a free body diagram showing and labeling the forces, not components, that are going to be none in the situation exerted on the passenger. So all we're going to do here is just see what is in contact with the passenger here, which when you're sitting on a seat is going to be the seat, obviously. And we have then the non-contact forces, which is my weight, always going straight downwards. So I'm going to start off here with my non-contact force, which is going to be weight, Fg. And that is straight downwards. The last time I checked, if I drop something, it's going to fall straight down. And again, when we annotate this for Fg, that is going to be the force of object on object. So the force of Earth, because that's the object, not the force of gravity, the force of Earth on the passenger. All right. Then we're going to have what else? Now all the other forces, my bad, are going to be in contact with the object that we're looking at. So for this, it's just a seat. We're not going to worry about like the back of the seat. All we're going to worry about is the actual seat that you're sitting on. that is then going to be pushing straight up on me or on the passenger. So that is going to be our normal force that is perpendicular to the surface. And we're going to say that this is the force of the seat, because that is the object, so force of seat on the passenger. All right, so those are our two forces. That's what we're going to end up having here moving forward. So we can now move into part B. All right, so looking at part B of this example, is the normal force of the seat on the passenger greater than, less than, or equal to the weight of the passenger? Indicate your answer down below, then briefly explain. So again, with any of these types of questions, I want to look at explaining everything first instead of just checking something off, because if I explain the physics that I know or communicate the physics that I know, I'm more likely to get it correct versus just checking something off and going based on that claim all the way through. Because if your claim is incorrect, you're just going to come up with physics that may not even exist to say that that is indeed correct. So all you got to do here is communicate what you know. And again, when we do these, I'm following based on the fact sheet that I have in the description down below. So feel free to go down there and download that along with the examples in Google Docs. They're both in the description down below, linked there. So for this, I'm going to start off here with my direction of acceleration, because direction of acceleration is important to know based on the direction in which forces are unbalanced. So I'm going to start off here with direction of acceleration since we are moving in a circle. So that fact is going to be straight from circular motion, and the fact that I'm going to have here is going to be that an object moving at constant speed v in a circle of radius r has an acceleration of magnitude v squared over r directed towards the center of the circle. So directed towards the center of the circle here is the important part. This is going to be my evidence yet again. But I have to explain this evidence further. So I'm going to need more evidence for this because I'm looking at the forces. So again, just to kind of think about what we're looking at here. So again, my free body diagram, I had FG straight downwards, and I have FN straight upwards on the passenger there. So this is what we're going to be looking at to kind of make the ideas now of the direction in which forces are unbalanced and things like that. We have the direction of the acceleration. So I want to go one step further and kind of put unbalanced forces or direction of the unbalanced force and direction of acceleration together. And the other evidence or the fact that I'm going to use for this is going to be an object's acceleration is in the direction in which forces are unbalanced. So we have more evidence here for this. So again, now direction in which forces are unbalanced, that just means that that side, if I have opposite forces, that side is going to be the greater force here. So I should kind of have an understanding of which one's going to be greater, or if it is greater than or less than the weight here, because the Fn is the upward force. I know at the bottom of the circle here, and I'm going to explain this in a second, that my acceleration is directed upwards. So that's how I'm going to make my reasoning here, since I am moving in a circle at a constant speed. And towards the center of the circle at the bottom is directed upwards. That means my acceleration is also directed upwards. So this is going to be my reasoning. So again, a full explanation. I'm moving in a circle at constant speed. Acceleration is towards the center of the circle. At the bottom, the center would be directly upwards here. So based on this, my normal force is the upward force. So I can make the claim that the normal force should be greater than my weight. So that is going to be my final claim here. And this means the normal force, which is in the direction in which forces are unbalanced, based on the free body diagram, will be greater than the weight, which is Fg, of the passenger. So that is going to be my claim. And you've probably felt this before in life. You've ever been on a roller coaster at like the bottom of a hill, feel a little bit heavier than you did at the top of it. If you've been in a car like this, you might feel a little bit heavier. So that's just the explanation of this, because when you're in a circle, those forces are unbalanced upwards. So you're going to have that greater force upwards compared to the downward force, which is Fg in this situation. So greater than is going to be my answer. So let's move into part C. Alright, so for part C, calculate the force that the seat exerts on the passenger as the car passes the lowest point of the arc. If you need to draw anything other than what you've shown in part A to assist you in your solution, use the space below. Do not add anything to the figure in part A. So this is something that is usually sent in an AP exam. If you have to draw a free body diagram, they basically will say don't add anything to it, because then you'll lose points, even though it might help you. In this situation, it's not really going to help you that much if you add anything. We don't really have components or anything like that here. So for this, really, whenever we deal with circular motion, it's just an extension of forces, essentially. So we're going to do the same exact idea as we would do when we have forces, just a regular forces question. But now our acceleration has an equation, which is the v squared over r. That's the only difference. So again, I'm going to show my free body diagram here on the side, as I have here Fg is downwards and Fn is upwards. And then I'm going to start off here with, since I only have up and down forces, my up forces minus down forces equals ma equation, which is the unbalanced force, or F net equals ma. I'm going to start off here with the upward force because we figured out in part B that my acceleration is directed upwards. So that is going to be Fn. So I'm going to have here again up forces minus down forces equal to ma. Alright, so my upward force is going to be Fn. So again, this comes straight from the free body diagram, just like when we do an equilibrium. So Fn minus Fg equal to ma. Now we're going to break this down one step further, and we're going to have here as Fn minus mg, since Fg is mg. And now we have our equation for acceleration in a circle, and that is going to be v squared over r. Alright, so now here, one last step, we're just going to do our algebra. We're going to move mg over to the other side of the equation. So that's going to cancel out on the left side. I'm going to be left with my normal force Fn is equal to m v squared over r plus mg. Alright, so now our answer from the previous question should make a little bit more sense, as I have here my weight mg, and I add something to it in order to get the normal force Fn, so that means that my normal force has to be bigger than my weight. So we explained it with words, and we can kind of look at it mathematically here as well with the equations, as the math and physics is just there to back up the concepts that do exist. So now from here, this is the AP exam and it said derive an expression for the normal force or something like that, you'd be done. But we have some numbers, some simple numbers just to plug in here in order to get our answer. So I'm going to plug these all in. So we have here the normal force equals the mass, which was 80 kilograms, times v squared here, which is going to be 10 meters per second, raised to the second power, all over 10 meters, plus 80 kilograms times g, which again is 10 newtons per kilogram, or some teachers like to use 10 meters per second squared. It's the same exact thing. So let's go ahead and plug this into your calculator here for a second, and then we're going to get the answer. Give me one moment for this. So we're going to have here 10 squared over 10. So obviously 10 squared is 100. Divided by 10 is going to give me 10 again. So multiply that by 80. So 80 times 10 is 800, plus 80 times 10, which is also 800. So you should end up with a normal force here of about 1600 newtons if you did everything correctly. I'm not going to show all the math from there because we did all the algebra already. The rest of this is just plug in stuff into your calculator to get the answer, which sometimes does come up on multiple choice questions on the AP exam. Alright, so we have normal force here that is clearly greater than my weight, so my math backs up my idea in part B, which the normal force is greater than the weight Fg. So let's now move into our second example. Looking at example number 2 here, where a block of mass m1 is tied to a string and is allowed to revolve in a circle of radius r at a constant speed on a horizontal frictionless table. The other end of the string passes through a small hole in the center of the table, and hanging mass m2 is tied to it as shown below. The suspended object remains stationary while the block on the tabletop revolves, so it just goes around in a circle. So for my free body diagram, I broke this up into 2 slides. As you can see in the examples in the description down below, it's just part A for the free body diagram. What I've done here is part A1 and part A2, just so I can fit everything on one slide and or not really like kind of squish everything on one slide, really. So for this, we have here block M1. That is the block that is on the table, so we can see that here. And I'm just going to create the free body diagram based on that. So what I have here, what is the first force that I'm always going to have? It is going to be Fg, and that is going to be straight downwards. And I know that Fg is the force of Earth on the block. That's the force of the object on the object. The first object is Earth, the second object is the block. So now all our other forces must be contact forces. So what's in contact with this mass M1 here on the table? What we have here is going to be the actual table itself. That is going to be pushing straight upwards because there's no angles, and that is known as our normal force. That is perpendicular to the surface. So what I have here is Fn, and that is the force of the table on the block. All right, so what other forces do we have here? What else is in contact with this block? The only other thing I can see in contact with this block is a string that is pulling here to the left, it seems like, based on the diagram that I have. So I'm going to make this force here straight out to the left, and I'm going to label this Ft for tension. So we have here F subscript T, and that is the force of the string on the block. All right, and that should be all our forces because we are only in contact with the string and the table, and our non-contact force here is Fg straight downwards. So let's move to block M2, or the hanging mass. All right, so take a look at our hanging mass here. This is the mass that is below the table right here, and it has a string attached to it going upwards as it goes through the whole of the table. So look at the forces that we have on this mass. We are going to have, obviously, the weight of the mass, that is Fg, that is going to be always straight downwards. So we have here Fg, and that is the force of Earth on the hanging mass. All right, so then all other forces have to be contact forces. So what's in contact with this mass? The only thing that's in contact with it is a string that is going to be going straight upwards. So I have here Ft, that is straight upwards, and Ft is going to be the force of the string on the hanging mass. All right, so now we have our free body diagrams for both M1 and M2. We can move into the rest of the example. So let's move into part B. All right, so in part B, which of the following vectors shows the direction of block M1's acceleration when it's in the position shown in the diagram? Circle 1 and then justify my answer. So now here with the block M1, which again is this block that is on the table, we know here with block M1 that is moving in a circle of radius r at a constant speed. So then I can start off with my fact of physics that explains circular motion for constant speed in a circle. So the fact that I'm going to end up using here is going to be an object moving at constant speed v in a circle of radius r has an acceleration of magnitude v squared over r directed towards the center of the circle. So that's going to be my evidence here for this situation, or my fact of physics. Now I'm going to explain this fact. I know this mass is moving in a circle at a constant speed, so that's going to be my reasoning here, that since the block or the mass is moving in a circle at a constant speed, that is going to be my reasoning. My then claim is going to be based on this, that the vector that best represents the acceleration is going to be pointing to the left, because based on the diagram, that is where the center of the circle, or that is towards the center of the circle at the point of the object's motion. So that is going to be my final claim here. The vector that best represents the acceleration of the block is pointing to the left, as based on the diagram shown, that is towards the center of the circle at that moment. So what we have here is going to be the vector here, the one that is pointing to the left. And again, just based on this diagram, if you want to take a better look at it, add the block there, and that's the arrow that points to the left at that point. All right, so let's move into part C. All right, so in part C, we're going to derive an expression for the tension and the strain in terms of given variables and fundamental constants. So which block are we going to use to actually do this? Which one do you think is going to be easier? With M1, the block that's on the table, I know that's moving at a constant speed, but I don't know what that constant speed is. It didn't tell me like the constant speed is v naught or something like that. So I don't really have enough there to actually deal with that. What I do know though is that block M2, which is the hanging mass, is stationary. So that means that it's at rest. So what do we do with an object that is at rest? We have an object that's at rest, we're in equilibrium. So that means we can use our up forces equal down forces. So let me just write my free body diagram again for M2 just so we can be reminded of it. So Fg downwards and we have Ft upwards. So with this, I can do the equilibrium equation. So we know that in equilibrium, up forces equal down forces. And again, I can use this due to the fact that they said that that hanging mass M2 is stationary, so that means it's at rest. So the up force based on this is Ft. This is the thing that we're deriving the expression for. Fg is the downward force. So then we're going to go one step further and say what Fg is, and that is mass times the gravitational field strength. And we would go one step further right now and plug in our variables, which are our numbers here, or numbers in quotation marks here. So the hanging mass, it was given to us as M2. So all we're going to do is just plug that in, and it's as simple as that for our expression for the force of tension, and we're going to use this in part D. So again, very similar to just plugging in numbers. When I have an expression, if they give me something like M2, I have to plug it in at the end there to get full credit for it. So let's move into part D of this example. All right, so moving into part D of the example, we're going to derive an expression for the speed of the mass on the table in terms of given variables and fundamental constants. So for this, we're going to use the tension that we had derived in part C. That is because when you have a strain that is attached to two masses like this here, it is the same strain, so it's the same tension throughout the system. We're going to see this more as we go through Atwood machines and modified Atwood machines and things like that. So let's remind us of what the free body diagram looks like here. So we're going to need it. So we have Fg downwards, you had Fn upwards, and you had Ft to the left here. Again, this is for the object on the table. So we're going to try and find the speed of the mass. we know that in circular motion that we have an equation for the acceleration of an object in a circle, and that involves speed. And we can then use Newton's second law because same exact thing here. We have F net, or unbalanced forces, equal ma, and that acceleration is the v squared over r in a circle. So with this, when we create our Newton's second law equation, we're going to start with the force that is in the direction of acceleration. We know that acceleration is to the left at this point, and we can see that Ft is the only horizontal force. So we're going to start off here with left forces minus right forces equal to ma. So as you can see in the free body diagram, there is no right force, so that's going to be 0. My left force, again, this comes straight from the free body diagram, is Ft, and that is equal to ma. And again, I'm using this because there is the equation for a circle for acceleration, that's v squared over r. So Ft, what we derived in part C, that is m2 times g. Our mass here is going to be m1 for the object on a table. My equation for acceleration in a circle, that's v squared over r, and the r that they gave us is capital R. Now I'm just going to isolate for v on one side of the equation. What I have attached to this is m1 by multiplication and r by division. I'm going to start off here with m1 first. Since it's attached to v squared by, or v by multiplication, I'm going to do the opposite and divide out from both sides of the equation. So I'm going to have here m2 times g over m1 is then equal to v squared over r. Now I want to get v squared by itself at the current moment. It's being divided by r, so do the opposite and multiply r on both sides of the equation. And then I'm going to have here m2 times g times r all over m1 equals v squared. So my last step here, since I have a squared on the right side, I want to do the opposite of squaring something, which is taking the square root of it. So we're going to do this on both sides of the equation, and I'll be left with my expression for speed, which is the square root of m2 times g times capital R all over m1, and that is going to be my final answer, my expression for the speed of the block on the table. All right, so that is the end of these examples. I hope they were helpful, and see you guys in class.